Welcome everybody to another episode of AVSO Presents. Today, this is back to our kind of webinar series after we've had the last series of webinars that have been focused on our sections. Now we're back to more general purpose webinars. And then today we'll be talking about the AAVSO-SNEWS campaign and featuring Dr. Alec Habig and AVSO's own Dr. Bert Pablo. So I'd like to just provide a couple of a little bit of information for you as we get going. So in case this is your first time participating in one of AVSO's webinars, just like to introduce you to some of the control panels that exist for the webinar series. So at the bottom of the screen, you can use the chat button to introduce yourself, and I've seen lots of people have been doing that thus far. If you have any questions during the presentation, please use the Q&A button rather than the chat button to type in your questions. That way I can find them kind of at the end of the presentation to ask people. And then Zoom also has automatic closed captions. So if you go ahead and click on the CC button and choose the spoken language, so in this case, English, it will automatically close caption the webinar for us. If you were here just at the very beginning, I'd just like to mention to everybody that this year's AAVSO annual meeting will be held down at the U.S. Space and Rocket Center in Huntsville, Alabama. As you can see from the graphics in the background, there's a whole bunch of really cool space-related things there, including a full-scale Saturn V rocket. There's both one that's set up out front, which is the large one that you see in here in this image, but in the building right behind it, there's a full-scale Saturn V that's laying on its side that's actually separated into its individual stages. It's a very interesting place to go. And so if you would like to know a little bit more about what's going to be happening at our annual meeting, go ahead and visit www.avso.org/113. And then I'd also like to thank our series sponsor. For this webinar, our entire series this year has been sponsored completely by Voice Astro. And I'd like to take a moment just to thank them and acknowledge them for their generous support. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools, and they help you learn how to perform observations, conduct research, and publish the results in scientific journals, much like the Journal of the AVSO. So please check out their website at voice-astro.org if you'd like to know more. So without further ado, I'd like to go ahead and get going on the main portion of our presentation. So today we're going to be discussing the SNEWS campaign, and it's actually going to be a dual hosted webinar. The first speaker today will be Dr. Alec Habig. So Alec, I'll go ahead and stop sharing my screen and let you share yours.
All right. All right. All right. Appears to have worked. Hi, I'm Alec Habig from University of Minnesota Duluth, and I'm a professor at that university, and will work with the SNEWS project, which is a meta project among particle physics experiments that could see neutrinos from supernova. So I'll tell you a bit about that, and then Bert will talk about how AAVSO is working on the same bit of science. It's pretty cool. And I see a few of you out there who are working with us, AAVSO people already. So, hi guys. Right. So of course this supernova and let's see, does the is the mouse working if I gesture at things? Okay, great. So this near the Tarantula Nebula in February 1987, this blue supergiant went boom and made the closest supernova to us that humans have seen since Tycho, and we saw neutrinos from it because we had proton decay experiments at the time that were large enough to see neutrinos. And so exploding stars, weakly interacting particles, and being prepared for what might happen next. So yeah, of course, a supernova as you all know, is a star that blows itself entirely apart, unlike regular nova, which we hopefully will get to see soon. And there are roughly two types. Type 1 doesn't have any hydrogen lines in the spectra, and they're mostly white dwarfs piling up enough extra stuff in a regular nova situation. They go boom. And type 2 have hydrogen spectral lines, and now we know what they are is cores collapsing in massive stars at the end of their life. And it's roughly 50-50, and there's some odd hybrid classes that happen when you have mass loss and things like that. So there's a supernova, of course. You all go look for supernova, and they're the star that wasn't there before that's as bright as the whole galaxy for a few weeks. And these are visible across the entire universe. Those type 1As, since it's always a white dwarf, and white dwarfs are mostly all the same or great standard bombs rather than standard candles that have let us discover dark energy, right? Map how the universe is expanding over time, because you can see them all the way across the observable universe. And there are many automated campaigns out there now which just shoot images of chunks of sky today and then tomorrow, next week, and subtract them. And if you do that, you can find supernova. And so supernovas at some place in the universe are being discovered every day, several times a day. But these are all extragalactic. As I mentioned, humans haven't seen one since Kepler in our own galaxy. 1987A was not technically our own galaxy, but it was right next door, right? So, okay. My rather dated cartoons here, but what's going on when a core collapse supernova happens? These are not the standard candle white dwarf ones. As a massive enough star that's massive enough to have the mass and pressure and temperature to burn progressively heavier elements and fusion in the core ends up in this kind of onion skin layers thing where the inner layers are hotter and denser and are able to fuse heavier and heavier things together and get energy out. And the last set that works is burning silicon and sulfur and producing iron. And because of the way the nuclear physics binding energy curve works, you can't wring energy out of making anything heavier than iron. And so the star rather rapidly over the course of the last days of its existence accumulates an indigestible core of iron that cannot produce energy to support itself. And when that iron core reaches a Chandrasekhar mass, which is the mass where regular old electron pressure cannot provide enough pressure to keep things from getting squished, it gets squished. And all the empty space is wrung out of the atom. The electrons are shoved into the nucleus, joined with the protons, turned into neutrons, and you make a baby neutron star. And that baby neutron star, of course, is this kind of the size of a city, 10, 15 kilometers, whereas that core of iron was the size of the Earth. And so you sort of kick the bottom out of the star all at once and produce an epic blast of neutrinos over the course of a few tenths of a second, because every time you take an electron and you shove it into a proton to make a neutron, you get an electron neutrino. That protoneutron star is so dense and so hot that even neutrinos, which are famous for getting through everything, being weakly interacting, can't get out. And they're sitting there in a seething pile of baby neutron star. And then the core gets as dense as it is, it bounces, it produces a shock. The shock starts propagating outwards through the star. And neutrinos help power that shock, and that shock rips off through the star, going from the central part of the star all the way out through the entire radius of the star, and eventually crashing through the surface, the photosphere, at which point we see the fireworks that we saw pictures of a few slides ago. And that's the explosion, and the star is ripped apart. All those elements that it made in fusion, plus a lot more from the just general violence of the explosion, get sprayed out into the universe, and so that's why we are sitting here made of something other than hydrogen and helium, because previous stars supernovaed and blew their carbon and oxygen and stuff out there for us to be made of many stellar birth cycles later, right? That's fun. And then that protoneutron star sits there, it's really hot, and it emits neutrinos. In fact, it cools for neutrinos for quite some time. Why do the neutrinos do this? Why does it cool for neutrinos? Neutrinos are escaping. Any other particle that might get made by pair production for just being so hot that you can make matter antimatter pairs of stuff doesn't go anywhere. It gets stirred right back into the mix. If you happen to make neutrino antineutrino pairs, they escape. So it's the leaky hole in the bucket. That's why it makes neutrinos. And the neutrinos from these phases actually make about 99% of the total neutrinos that we see. That first burst you think of by making a lot of neutrons is very spectacular for a few tenths of a second, but the total number of neutrinos is dominated by we're just making a lot of neutrinos because it's really hot and it's the only way the energy can get out. And so this makes a supernova, core collapse supernova, a really interesting target for multi-messenger astronomy. If you are watching that progenitor, say a 17 solar mass Betelgeuse thing that is one of the brighter stars in any given galaxy, here it is, over time just being really bright. That's really bright. That's a log scale in ergs per second. And you see it being really bright, nothing much going on until all of a sudden, boom, the shockwave rips out through the photosphere and you see a supernova, a new star that dims over weeks, and you can follow it and get light curves, and all those supernovae that we see in photons are doing that. However, notice a couple things. One, when that star, before it explodes, when it's burning, the silicon at core is so hot that it's cooling by neutrinos, and many orders of magnitude more energy is leaking out of that star in neutrinos. And then at the point where it does collapse and explode, this is a log scale. Look how many extra zeros you have for the total amount of luminosity squirting out of this exploding star in neutrinos, and that happens minutes to hours before the shock wave travels that radius of the star, hits the photosphere, and we get to see photons. And so these lines are all neutrinos, luminosity neutrinos, and it should also make gravitational waves, because you take a really, really heavy thing and you slosh it around. If it collapsed perfectly spherically symmetrically, you won't get gravitational waves. It has to have some instabilities and slosh about, and exactly how that works is uncertain. This is an example amount of energy being released in gravitational waves, which is still many times as much as the star itself, but not nearly as much as the neutrinos. So lots of things are going on here. This is a gravity-powered neutrino bomb is what they are. 99% of the total energy of the supernova explosion squirts out in the form of neutrinos. 1% is kinetic energy. You've all seen pictures of the Crab Nebula, for example, or Cas-A expanding over time. That's a lot of kinetic energy from supernova remnant. Only 0.01% of the energy is that supernova blast that you see with your telescopes that are fun to take light curves of. It's totally dominated by neutrinos and a little bit of just explosion and maybe gravitational waves, depending on how sloshy it is. So, and we know this is true as opposed to just a good idea. Hans Bethe was one of the people who first came up with how well this might work. And in 1987, there we go, there's 1987A. It was a core collapse supernova in the LMC 55 kiloparsecs away, and that was so right next door, it was very well studied. And of course, Murphy's Law being what it is, it also was a really weird supernova. It was a blue giant instead of a red giant, had an odd dim light curve. But most importantly for science, it was close enough so that the 1 over r squared that spreads out and makes luminosity decreases r squared over distance didn't crush the neutrino signal, and it was seen in the neutrino detectors. And here is data from 3 of the ones that claim to see it. The 4th one, it's a little ishy whether or not they actually saw it, but there it is. Over the course of 10-ish seconds, they saw a bunch of extra neutrinos that were not consistent with background, and those neutrinos had kind of tens of MeV worth of energy, which is what was predicted. And you work backwards from the number of neutrinos that were saw and the size of the detectors that were looking at them, and you get about the right amount of energy when you 1 over r squared it back to the explosion. So they walk like a duck, quack like a duck, and we saw this explosion. Exactly when the delay between this and the photons that were saw was a little unclear, because this was found after the fact, after I'm going to forget the name, so I won't try. The observatory operator at Saratoga walked out and said, "That star's not supposed to be there," on a smoke break. So you know it was there then. And beforehand, they went to amateur astronomers around the world and said, "All right, who was watching the LMC at what time?" And they were able to establish that it was kind of maybe an hour and a half between the neutrino signal and the light signal, but that was no one knew for sure. This was yep, didn't see it till then, stopped looking, that kind of thing. And this was old enough that graphics for high energy physics experiments looked like this, straight from Tron. This one was underneath Lake Erie in the Morton Salt Mine, IMB. And those neutrino data in the particle physics detectors let us know that nearly all the energy coming in neutrinos bit about core collapse supernova is really the way it works. Today, if we pick a random round number within our galaxy, say 10 kiloparsecs away, with modern detectors, which are much larger and more sensitive, instead of seeing dozens of events, we'd see thousands. And we learn an awful lot about many things, both particle physics, and you have a window right into that birth of a neutron star, right? You're watching the neutrinos coming streaming off of that. We learn a lot about astrophysics as well. Now, of course, we haven't seen one since Kepler, and of course his boss Tycho saw one, and we haven't seen one since. How many supernova are going to be in a Milky Way-like galaxy? There was a good paper that looked at a lot of different ways you could measure this by looking at similar galaxies mostly, and the answer is kind of 1.5, so 1 or 2 per century per Milky Way. And people have seen remnants of supernova which are younger than Kepler's. I think Cas-A is a good example of this. So we know they have happened, but if they're happening right behind a different spiral arm and we don't see the photons in the 1700s or whatever because we didn't have other ways of seeing things, humans wouldn't see it. So the key thing is these neutrinos give you advanced warning, right? They get out as almost as soon as that core collapses and that neutron star is born. Whereas the star itself, and here's a picture of a familiar star where we have a good view of the photosphere, would just sit there looking like that until that shock wave rips from R equals 0 to R equals stellar radii and blows out the photosphere, and then you would see the photons. Of course, the sun, of course, is far too small to do this. It'll piddle out with a white dwarf and a planetary nebula. But that's the only picture of a photosphere I had. The ones of Betelgeuse are kind of not as compelling. All right, so we're going to get hour-ish for a compact blue progenitor, a Wolf-Rayet star or something, and maybe 10 hours or even more for something like Betelgeuse, a big red supergiant, just entirely to shock travel time across the radius of the star. So if we get neutrinos that are consistent with that signal that we saw before from 1987A and modern detectors, we know a supernova in our galaxy has just happened and that some star in our galaxy is about to go boom. And we could get ready for it and get good data on it as it explodes, as that photosphere rips apart, ideally, or soon thereafter, and what happens when that shock wave goes tearing off through that poor solar system, or the clouds of gas that star has blown off in mass loss events recently, things like that. Would be a lot of fun. So how to do it differently next time, rather than saying, oh, look, that looks like a supernova, let's go look at the data from the neutrino detectors, which is the way it happened before. You've heard it, luck is opportunity times preparation, right? I say it's probably opportunity crossed with preparation because it's always at right angles to what you think. But if we're prepared for it these days, we have neutrino experiments around the world that could see it. We're all watching for it. And how could we get the word out so that people, when other messengers, photons, gravitational waves, different kinds of photons, gamma rays, X-rays, whatever, could get observations from as soon as possible, as close to the beginning of the explosion as possible. We have a prayer of noticing whatever cool things happen when that explosion happens. So instead of going and saying, hey, neutrino detectors, look at that astronomical telegram and go dig through your data, which in 1987 happened, let's do the reverse. Let's go out and look at things with photons because neutrinos were seen. So supernova could be seen in a neutrino experiment if that experiment can identify that that burst of stuff isn't just noise, or someone opened the tank and light got in or whatever. Hey, that looks like a supernova. Get the word out. The hard part, figure out where you should look, and do this all in about an hour. And an example is over the past couple decades, the GCN Bacadine network has done this in seconds for gamma ray bursts, and they've had a lot of practice because you get about a gamma ray burst a day. But now we know what gamma ray bursts are, both types, the fast ones and the slow ones, and that's just entirely due to this same kind of scheme of let's go out and look whatever we can at the explosion and learn about it and catch them in the act. And gravitational waves is doing the same thing. We've seen a kilonova, right, where two neutron stars smashed together, made all sorts of interesting elements because a gravitational wave said, hey, go look over there, and people got other telescopes turned on it. So this is the basic scheme. Why a network? Any one experiment has many sources of noise and few supernova, right? None recently, and maybe not 1 or 2 per century. Many things can make things in your detector look like a supernova. And most, if we go and whoever is on shift or gets woken up, and this picture of a pager we actually used for getting woken up by our supernova trigger back in the day before cell phones. Yeah, okay, all right, yeah, that's that photo tube over there. Or, oh, high voltage freaked out, whatever it might be. But no experiment would want to make that automated announcement on their own. But different experiments around the world are going to have supernova neutrinos at about the same time and not going to have random light in the tank. And so a coincidence will help eliminate that and give enough confidence to do it automatically and fast. And SNEWS currently has these 5 experiments, although Camland is currently down for renovations, contributing their supernova triggers to this coincidence network. And this has been going for 2 decades now. Many experiments, which are now completely gone, participated, and others are in testing, and new experiments all looking to plug in as they can do it. So this is really simple. It's old C code from 1990. Actually stole from a side project as a graduate student, which is NetTrek, one of the first esports games. So I justified my immense amount of time in grad school wasted playing video games by recycling the network code. and the different experiments send a packet. And a server says, 2 experiments saw something interesting, let's tell the world. And there's an email list, because this was 1990, this is what we do, that's how you notify people with emails. And we also, different experiments that are interested in getting things right away, get a dedicated packet. For example, gravitational wave experiments, if they know right when a supernova happened in neutrinos, are much more able to pick up on whatever random shape it is, because no one really knows how sloshy that neutron star is. So this has been a couple decades. What can we do? The idea was, wow, this code is crunchy. It's really hard to compile on new systems and add to new experiments. Let's rewrite it. Let's do modern stuff. What else can we add? Well, now that we're all used to multi-messenger astronomy and alerts happening from gravitational waves and neutrinos and high-energy cosmic rays and whatever, people aren't as worried about a false alarm as they were when we started. When we started, the astronomers told us, if you ever give us a false alarm, we're never believing you crazy wolf-crying particle physicist again. So we're really, really, really conservative. Now, people say, yeah, tell us on something marginal because we want A, to be able to see something cool that might be real. We're used to it. And B, if you do this, it tests the system and we know that it all works, as opposed to waiting for 20 years and hoping that it works. So where we're at now. So we want to do that with the thresholds. We want to be able to compare the data on the fly to extract physics quickly that will help. Particularly, I'll show you in a minute, triangulation of where it is on the sky and maybe how far away it might be with some error bars. And many networks exist now, and using modern tools will help us better coordinate with those networks. So we also hope to be able to take experiments, those which are sensitive enough to detect the very faint and weak and low energy signal of the silicon burning, the pre-supernova neutrinos. That's feeble enough that we can maybe get out to a kiloparsec if we were to combine the different experiments' marginal signals. And so that's something we could do. Combining signals is what SNEWS has been doing for a couple of decades. And pointing, either from timing, show you in a second, or experiments that can see where the neutrinos are coming from, we can start stacking them on each other and creating ever better error boxes that we could keep updating people with. So 2 experiments, one that exists, one that I'm working hard to make exist, can do this now. Some small fraction of the neutrinos that a super K can see actually have a direction. This is the way super K sees solar neutrinos. And so if you can fish out that extra little blob there from all the rest of them, which Mother Nature doesn't color them red and blue, but statistically you can actually do a pretty good job of this and get a kind of 4-degree half-angle cone a little better now, because they have able to tag some of the green ones by doping it with gadolinium. And for a long time, we thought this was the only way we'd be able to do it. But we started looking more carefully at a higher statistics experiments. Oh, this, by the way, is, you've seen this before probably. That's the core of our sun seen with neutrinos from super K, from solar neutrinos, with the caveat that each pixel here is a half a degree, and of course the sun is a half a degree in size. It's really blurry. You can't upgrade the physics of how well you can see neutrinos and get their directions. That's particle physics. But what you can do is you can say, hey, I have 2 different experiments here, and if that supernova explodes, that wavefront of neutrinos is going to hit this one first and then that one, right? And getting the angle depends upon how well you can say exactly when did the neutrinos reach here. The more neutrinos you see from the bigger experiment, the closer supernova, the better timing you can do. This is exactly the way LIGO does gravitational wave pointing. By when did the gravitational wave reach different detectors in either LIGO, Virgo, or now around the world as more and more detectors happen. The more experiments you have, you get to narrow it down. Here are 4 smaller experiments. You can say, wow, that's the whole sky. That's really kind of bad. My telescope doesn't have that field of view. You add in IceCube at the South Pole, which is really big and has high statistics, and pow, suddenly it's an error box that you can work with. And we have a map of red supergiants that we can see, not all the ones in the galaxy, of course, but a pretty good catalog of ones nearby, that if it did explode, we could say, hey, we sort of know how far away it is because we can do 1 over r squared. We know what a supernova does, and a direction. And in this case, this test explosion of that particular supergiant, which you can go find if you want, do the calculation with the neutrinos and makes an error box between the experiments that we simulated, and there are 105 stars in that angle, but only 3 that match if you get a distance estimate. And so we might be able to say, these are the hot topics. It could be one of these stars. Let's watch it. Let's watch it explode. So that would be cool. And that whole catalog and what we're doing with that, that's what Bert's going to talk about next, and get a pre-supernova baseline and get eyes on target. So I won't talk about that because that's what Bert's going to talk about next. So in summary, you can think about this 2 ways. Oh man, 1 or 2 supernova a century. I hope I live that long. Or you can say the supernova, this galaxy is a big place. There are already 200 stars that have exploded, and those neutrinos are headed towards us at the speed of light. That's more exciting to think of it that way. And we are prepared to watch them and tell people something happened, hopefully where it happened and how it's happening, and really learn a lot about the next supernova. So that's what I've got, and I'll pass it over to Bert now, who can talk about what you guys are doing to help this quest.
Thanks, Alec. Give me 1 second to share my screen. I can't get prepared because I cannot share screen until you stop sharing. So it's one of those where I have to wait, but okay, yes. Just wanted to make sure I wasn't still muted, because that would have been problematic. Hello, everyone. So Alex gave a great overview of the SNEWS project and what they are hoping to accomplish from the particle physics side. And I am going to talk a little bit about what the AAVSO is doing and how it's involved in that effort. And to sort of introduce that idea, I'm going to sort of start from a baseline that pretty much everybody knows, and that is T-Core Bohr. So if you are part of the AAVSO community and you attend these webinars a lot, there's almost no chance that you have not heard this name before. I see articles on this star pop into my feed once a week, at least. So it is a topic that is hot in the astronomical community in general. And there are a lot of good comparisons between T-Core Bohr and what we're trying to accomplish with the SNEWS project. First of all, if you don't know what T-Core Bohr is, it is an interesting star that has a recurring nova. So that means it explodes. Not as big of an explosion, but still an explosion. And that explosion happens about once every century. So just like in SNEWS, it's a very fast event that only happens over a brief period of time, and you want to catch it when it's happening. You have some degree of forewarning about the event, as Alec talked about with the neutrinos. That gives us some forewarning of this event. With T-Core Bohr, we actually have quite a bit more. We know from the light curve certain things that indicate that something is going to happen within the next few months to a year-ish time frame. Like there was some idea that this was going to happen. Exactly why I'm not going to get into because it's not super important. And as you can see, these are fairly rare events that only happen occasionally. However, there's quite a few differences as well, which sort of define the project. The first is that while in the case of T-Core Bohr, there is forewarning of somewhere in the neighborhood of months to potentially years, we have hours, right? It's not nearly as long. We should know that it's going to happen, but we don't really have much more than that. Supernovas only happen once per star. So unlike novas that can be recurring and can happen multiple times and you can predict them, we don't really know what star is going to go supernova, and it's not an event that you can predict. So you have candidate stars, but once it happens once, you can't stay on that star and hope that it will happen again, because obviously it won't. And to go along with that, unlike T-Corp, where we know exactly what star it is, there are lots of progenitor systems that could be a supernova. There are so many, in fact, that we kind of have to pick and choose. There are roughly 600 red supergiants that made the initial cut. And we are not even looking at all of those, but I'll get into that a little bit more later. So since there is this problem with forewarning, right, where we don't have a whole lot of time, how do we go about doing this? Well, as Alec talked about, there is now a network that can produce these alerts and send them out to people. The AAVSO community, or really anybody who wants to, can get these alerts. You can sign up on the SNEWS fire drill. There will be a link that I can send you later as to how to get here. But effectively, what this allows you to do is when the alert comes out, you can get it immediately if that's the kind of thing that's interesting to you and you want to be one of the first on Sky to view an event like this. You might get an hour's warning. You might get a few hours warning, but it's one of those that, you know, when you get it, you get on Sky as quickly as possible. And additionally, more than just the alerts themselves, there are things that are called fire drills, where they will simulate an alert happening, and you can sort of practice, or the community as a whole can practice and see what's going to happen there, and see what would happen if an alert like that came up and what you would need to do. It's just a good way of sort of being prepped for the event when it does eventually take place. And the other thing that we can do is we can have a baseline of these stars before they explode. Right now, there's not a whole lot known about supernova progenitors because in almost all cases, the supernovas happened outside of our galaxy that are known in history in one form or fashion. So we have never really studied the star ahead of time. We see the explosion, but before that, it was too faint, so we didn't see the star itself. Most of the supernova that we have are like that because they're millions of light years away. Well, potentially millions, maybe a little bit closer. But supernova 1987A is one of the closest ones, and it was still outside of our galaxy. So, like I said, we have to pick and choose. How do we pick targets? Well, we chose the targets that are bright, and we chose them to be brighter than 10th magnitude as our main focus for two good reasons. One is that these are the sorts of stars that are very difficult for surveys and other things to look at. So there will be much less data on them. So it's a great place for the AAVSO community to look. And also, they are the easiest targets to get more data on. So if you wanted multiple filters, if you wanted spectroscopic data, if you wanted anything else, the brighter the object, the easier it is to get that accompanying data. Now, these stars in general are red supergiants. That's what was picked. That means they have very, very long timescale variations, and we'll get to why that matters in a bit. But the overall point of our observations right now is to get reasonable coverage on as many of these stars as possible, so that when one of them does eventually go supernova, we have a record of what happened before. Kind of like what Alex said with supernova 1987A, you can't go back and see what was happening if you don't have the data to do so. So once one of these stars does go supernova, maybe we don't get any sort of indication in the light curve that tells us this is definitely going to happen. But when we look back at it, we can say, oh, okay, these are some precursor things that we can notice and study going forward. So where does the project sort of stand? Well, we've gotten a lot better recently. If you look back at the end of April, this is sort of where we stood. We had observed about 162 of these 192 objects, which is pretty good, but we were still missing some. We had roughly a third of them that were really healthy, so they were getting enough observations, often enough for it to be useful. And in total, we had around 7,000 observations in all filter bands. And more recently, I did these statistics to the end of June. And as you can see, we have significantly closed the gap. There are only 4 stars that have yet to be observed, which is a plus. When I say observed, I mean specifically in the V band, but just in general, I'm trying to sort of use that as a baseline. Some of these stars may have been observed visually, but most of them have not been observed at all. We have increased our healthy targets, so we're up to 114. That's still not perfect, but we're getting much better. And we now have over 9,000 observations in all filters. So reasonable progress. And what do these light curves look like? Where are we right now? Well, I find that the light curves sort of fall into 3 categories. The first are these stars that have not changed a lot. They are roughly constant, as best we can tell, over the course of what we have observed them for. These are so-called boring light curves. That doesn't mean they're not important. It just means that they have not done anything yet. Second are these stars with this sort of long scale variations. Now, these stars, if you'll notice, the time scale here is since the beginning of the campaign, so over 250 days, and especially in V386 SEP on the left, you can see that we haven't gotten through any sort of cycle at all. It's still going down. So these sort of long scale things, it's important to monitor for a long time. And we're only about 6 months into the campaign at this point, so we're still relatively early, but it's these sorts of things that are useful moving forward because of how long scale these variations are. And the third thing are some somewhat unique objects or things that really weren't quite expected. We don't have enough data to say for sure that they are particularly interesting, but it's worth noting some things. So the one I'll point out here on the left is this ASAS object with a long telephone number. And what's interesting about it is that for the longest time, it wasn't observed. I finally got someone to observe it starting last month. And in that month, we can see that it almost has one full cycle of some sinusoidal variation. Now, normally that wouldn't be that interesting, but the thing to note here is that typically supergiants don't have variations on the order of months, on the order of a month or less. Typically, their variations are significantly longer. So this sort of thing is unexpected, but still pretty interesting. It's these sorts of things that we don't really know because as a sort of class, supergiants haven't really been studied in depth. So there might be things that we find that are unusual, or it could just be that this is a small blip in an otherwise uninteresting light curve. We still don't have enough data to say. So I've talked about long-term monitoring a lot. And the idea here is that it provides a lot of benefits. One of the main ones is, like I said, once a supernova goes off, we can look back and see what was happening. But also, it allows us to sort of see what these stars are doing in general, to learn more about red supergiants as a whole. And to emphasize this point, we'll talk about probably the most famous red supergiant that there is, and that is Betelgeuse, or Alpha Ori. Now, if you look at the light curve here on the left, this is just the data taken during the SNEWS campaign. What you can see is that for roughly 100 days or so, it was relatively flat. Then there was a fairly significant dip that happened. It came back up, and then it's starting to look like it's going to dip again. Now, I don't know if anyone remembers, but around 5 years ago, everybody was really worried or interested in Betelgeuse because it had a fairly significant dimming event, dimmer than it had been in a very long time. And people thought that that might be an indicator that it was going to go supernova. Now, if you look at just this piece of the light curve, there's not much that you could tell. But when you look back, this data goes back about 7 years. You can sort of see why people made that assessment. The big dimming event that happened is this one right here in the middle. And it eventually did come back up. And if you look at the full cycle over decades, this sort of thing is not that uncommon. But when you just have this tiny fraction of time, especially on these stars that change on very long timescales, there's only so much that we can do. So having this data for long periods of time really helps us build a baseline on these stars to understand what they're doing. So the inevitable question is, how can you help? Well, there are a few different ways. The first is to stay informed. If you're interested in the project, you want to know what stars are useful to observe, where you can be of the most benefit. We have a AAVSO community Slack channel for SNEWS, which you're more than welcome to join. We have quarterly meetings where we sort of discuss things and sort of give an update on the project in a little bit more detail than I'm doing here. And hopefully, we will have a mailing list coming soon, which will give you information on various stars and their health, which you can sort of see in this little box below. Just some statistics of what's happening with each of the stars and whether or not you can observe them. I want to point out that in particular for this campaign, visual observations can be a big plus because there are certain stars which are extremely difficult to view with CCD or digital observations because the star is extremely bright. One good example is LCAR, where the data is the change is high enough that it's very easily seen visually, and also it's so bright that it's very difficult to view on a CCD without saturating. So a lot of these targets tend not to get observed. And for that reason, visual observations are actually really useful in these sorts of cases. And the more people observing it visually, the better the light curve is, because we have a lot more points that we can compare, and you can only look at a star like this every so often as a singular visual observer without biasing yourself. So the more people that we have in general, the better the light curve overall becomes. And finally, outside of just your typical telescope that you can observe with yourself, if you don't have one and you happen to be a paying member of the AAVSO, there is another option, which is AAVSO-Net. Typically, this is our series of telescopes that we allow people to propose to. In the case of SNEWS, it made more sense to just create a giant campaign and allow people to subscribe to it. So what you can do is you can tell people that you're planning to observe if you have your own telescope, or if you want to subscribe to AAVSO-Net, you can also do that. Then all of the images will be sent directly to you, and you'll have time to, and then you'll be able to take the observations and submit them yourself. And we actually do have some stars that are unclaimed currently this way, so there's a good place that you can actually do stuff. And that is it for me. So at this point, I think Alec and I will both be open to questions.
Yeah, thank you very much, Bert. Those and Alec as well. Those were both very interesting talks. And so I'm going to abuse my role as the host just really quickly and ask a particle physics questions to Alec. So it's been about 10 years since I've studied any kind of particle physics. And you mentioned, of course, that our electron neutrinos are escaping from the core of these things. Do we expect to see neutrino oscillations? And if so, would there be any kind of like dispersive effects between the different flavors of neutrinos in terms of like time of arrival?
Yeah, so we expect to see strong oscillation effects inside the star itself, the same MSW effect that we see in the solar neutrinos. By the time they get out of the star, they have decohered enough so that sort of their flavor composition is frozen in. So we don't have to worry about how far away they are if affecting the oscillations, but they get the imprint of the density of the matter they pass through on the way out of the supernova to us, which of course is extremely cool.
Oh yeah.
And the dispersive effect, and this was looked at in the 1987A things, if the different neutrino masses are different, are large enough, and the difference between them large enough, then we would see a dispersive lag in the neutrinos arriving. And that was not seen in 1987A and let us set a limit on the massive neutrinos, which was pretty good for electron neutrinos, but 20 eV. The dedicated tritium experiments are getting to tenths of an eV now.
Okay.
But we
Yeah,
would
so
be
we
able to
just
tell things like that.
yeah, we just need to wait for another one, I guess.
Yeah, we could tell a
Um,
lot about that. We could tell which neutrinos are heavier than others, for example, which we're currently having to build giant experiments to maybe figure out. Supernova goes off, we'll know it.
yeah, terrific. So I'll first get a question again for Alec, actually, from Timothy Weaver. He asks, wouldn't electromagnetic radiation also cool neutron stars? And if so, what percentage of the cooling is from electron neutrino emissions versus the percentage of cooling from electromagnetic radiation?
Yeah, to start off with, when the star is hot enough to pair produce neutrinos, it's nearly all neutrino cooling because there's so much stuff in the way that it blankets it out for electromagnetic. It's insulated. The EM radiation doesn't get out. Now, if you go look at, say, the Crab pulsar, that's no longer being cooled by neutrinos. That's electromagnetic cooling. But
Oh,
for the maybe couple minutes after this neutrino or the star is born, it's nearly all neutrinos doing the cooling.
yeah, oh, that's really cool. So next up, we'll pick a question for Bert here. So Patrick Kavanaugh, he asks, of the hot list of 192 objects that you're following in this campaign, how many of them are of magnitude 12 or brighter?
They actually all are. So the original list, I think, goes down to, I'm not quite sure, I think 14th magnitude. I'm not 100% sure exactly what the cutoff for that is. For the objects that we chose, we specifically chose those that were 10th magnitude and brighter. And the reason we did that was two reasons. One, that was where we thought we could make the most impact. And two, we needed to make cuts somewhere because 200 stars was already quite a lot to sort of try for this sort of campaign. And we're doing pretty well. But, if we had tried to like make this 600, which is the total number that is currently there, it would have been virtually impossible to get enough data on all of those targets to make it worth it. We might extend at some point to catch
Mhm.
more objects if we get a lot more interest and things like that. But for right now, that's where we stand.
I think you said the list was originally like 630 potential objects or something. So paring it down to a couple hundred is pretty good. Um, so this question, I think, could either be for Bert or for Alec. Rodney is asking, given that you said the neutrinos can kind of oscillate down, sorry, not oscillate, but isolate the area of the sky down to a few degrees, what is the ideal field of view and resolution for amateur telescopes that would actually be useful?
Um, do you want to take? I can answer something, Alex, but it kind of depends.
Yeah. So to start off with, although we might be able to say those several red supergiants are going to be pretty interesting, we mostly still have these enormous error boxes, right? Kind of gravitational wave style error boxes where we have many hundreds of square degrees, perhaps. And so in that case, wide fields of view that you could just shoot tiles of, so that we have pictures of something over there. So, all right, so we have some baselines would be fantastic. For example, the Zwicky Transient Facility is a robotic telescope which does this, chasing transients of all sorts, and they automated tile up really wide fields of views and just hope they catch something. So yeah, I think the answer is whatever you want to throw at it. Until someone sees some photons from it and can nail it down to arc seconds, the wider the field of view is probably better.
Yeah, terrific. All right, so then we actually have a question from Heinz Bernd Eggenstein. He's the chair of our high energy section here within the AAVSO. He asks if there's going to be regular tests of the alarms for SNEWS 2.0 like they are for SNEWS 1.0 over the near future, and will people actually be able to practice responding to these types of events?
Yeah, so the tests for SNEWS 1.0 are pretty simple clockwork, kind of like the tornado siren tests here in the U.S. They happen once a week at a given time, just so that we know the plumbing works. What the more interesting ones are, we've done a few times, and he's helped with this, is we say, all right, let's toss out a test where we simulate a supernova, and you guys go find which of those stars we might have pretend exploded in the computer, right? And that sort of thing, we have plans on doing. We did a smaller scale test a few months ago, and hopefully later this summer or fall we'll have the next one. And those kind of fire drills are something that we want to do semi-regularly for several reasons, so that we make sure all of our stuff works, right? And because it's fun, and to go out and find this thing. Does it work for you? So
terrific. Yeah, no, it's these things occur so quickly, right? You don't want to be fumbling over things, so having that kind of training is actually really quite important. Then there were a couple of questions here at the kind of the bottom of the Q&A box. Bert, I'll pitch these over to you. They basically are asking, where can we find out more about the SNEWS project on the website, and where is that list of 20 objects that we'd like to have observed?
And by 20 he means 200.
Well, yeah, I think they were referring to the ones that are left within AAVSO-net that aren't claimed. Yeah.
Oh.
So if somebody wants to learn more about both the SNEWS campaign as well as these objects, is there like a single page that people could go to learn a little bit more?
Yes, someone put it in the chat already. Enrique did, but I can share it as well. So it's the avso.org /snooze-campaign. And this page will have all of those links. It has quite a bit of information. So if you want the spreadsheet, you can go here.
It's under the target list heading there.
Yep, under the target list heading, and you click this, and that will open up the spreadsheet. And the fire drill information is listed towards the bottom. Yeah, right here. So, and then there's a few other things that you can get. Everything that you should want should be on this page, with the exception of a mailing list, because I have not put it together yet. So once that does exist, something like that will either be added to this page or somewhere else, but most likely somewhere on this page is where it would belong.
Oh, terrific. Thanks, Bert. So then we have a question here from Jeffrey Kassoff. He says, what fraction of the estimated 1 to 2 galactic supernova per century were obscured in the visible spectrum by dust and gases that got in the way? And would neutrino detection be affected by those types of observations?
Yeah, see, I have a cool graphic I stole from an old Sky and Telescope issue with this, if I can find it real fast here. The answer is about a 6 would be visible to the naked eye, and then the rest would have some amount of dust obscuration leading to a lot of them you just can't see, right? And the neutrinos don't care. The neutrinos are getting out of the core of the sun to our detectors right now, and uh, they go right through everything, which makes them very useful for seeing things that are far away behind things. And of course,
Mhm.
that's also simultaneously what makes them very hard to observe because it can mostly go right through our detectors too. And I'm sorry, I don't have that. I don't have that graphic handy. I thought I did. There's a nice pie chart of the of the of of the galaxy and the historical supernova, which is pretty enlightening. I'll dig it out here while I know where it is, but I won't.
Okay, yeah, if you find it, before the webinar ends, just we can go ahead and bring it back up. So while you're looking for that, I'll go ahead and pitch another one over to Bert. And Rodney Hughes is asking, since these events are relatively short, what types of filters would be useful in terms of collecting data? And there's the initial rise, but there's actually a pretty long decay time for a lot of these. So I'd imagine multicolor photometry would be possible.
Um, yeah, the truth is that once the event happens, you want it in as many filters as possible so that you get as much information as possible. If you could also take spectra, that'd be great too. Basically, the more data, the better in those sorts of situations. If you're not able to take or you only have a few filters, I would probably say V first and then probably B and R, um, but that's just kind of a guess. I don't really know what will be important. I don't think that anybody really does. So that's what I would say. For the monitoring project, we've been mainly sticking to the V and visual just because it allows us to get as many targets as possible. Trying to get multicolor photometry on 200 stars on a regular cadence becomes a difficult sort of problem to solve. So that's kind of why we chose what we did.
Yeah, no, that's fair. Then there was a question here from oh, actually, I think I just lost it. Oh, you found the
Oh,
graphic,
sorry. Yeah, I just
Alec.
popped
Yeah,
that up.
go
So
ahead. Yeah, go for it.
here it is, and I wasn't bright enough to write down the issue here, but this is like a 20-year-old issue where Leaf and Friends did an article about SNEWS and made this map with historical Milky Way in the galaxy, and it's an old scan, so exactly which one these crosses are which isn't easily readable. But there is a kind of a histogram there showing percentage of estimated of supernova that would be between what magnitudes.
Oh, terrific. Yeah, no, that's actually a really quite useful graphic. So,
Yeah, I need to
um,
go dig out the actual issue and get a better scan.
yeah, well, and then they have a lot of their issues online now, so you should have a
Oh,
pretty
okay, great.
yeah. So you should be able to get a much higher quality graphic out of the online edition. So there's another question for Alec here. Going back to your presentation, there you showed that picture of the sun, right, in
Hmm.
neutrino emissions. And the question is, if you're supposed to have a half degree per pixel and the sun is about a half degree
Yeah.
across, why does it appear so dispersed? Why isn't it just a single pixel in size?
Because that's a plot of the direction we see the neutrino coming from. And so when the neutrino comes into the detector, it bounces the electron that we see off at an angle, which can be random. And so we see, well, the electron came this way, so neutrino might have came from over there, even though it came from over here. And so it's just a really big smearing. Now, you can find the center of all that pretty reliably. So we can tell where the sun is pretty reliably, and we could tell where a supernova is given those statistics pretty reliably. But the blur factor of just looking at that in terms of an image with sharp edges is interestingly weird.
Yeah, no, that was actually a really cool image as well. To just imagine that you can actually see the sun. Well, like get an image of the sun in neutrinos.
Yeah.
That's absolutely wonderful that we can do that now.
And actually,
So
it's only the core of the sun that's making those neutrinos too. So that's a lot less than a half a degree. That's
approximately how big is it?
it's about 10% of the radius or less. So I guess 10% of a half a degree, so 0.05 degrees.
Okay, yeah, so 50 milliarc seconds or
Yeah.
so. Yeah, so that's pretty small. But, So Bert, another question for you. Paulo here is wondering if any of these objects are already in the AVSO spectroscopic database, and would it be useful, maybe this is for both of you, would it be useful for there to be spectroscopic data available before an eruption occurs?
So the answer is yes, there are definitely objects in there that are in the AAVSO spectroscopic database. I have not run the numbers on how many. It definitely is useful. It's just a lot more difficult to do the sort of baseline for spectroscopy than it is photometry. It's just a lot harder to keep track of. So having a spectrum would be great. Having lots of spectra would be even better. But, it's not the easiest thing in the world to do, just in general, because for spectra, you're kind of limited, like magnitude limited in the sense that for most of these, unless you're doing slit the spectroscopy, which does have some value, you're limited to 10th magnitude, most likely 8th magnitude or less, unless you just happen to have, a half-meter plus telescope available to you and, hours to sit on it.
Yeah, terrific. Yep. And next question again, back to Alec. I keep bouncing back and forth between the two of you. So Brad Schaefer, who is our kind of resident T Corona Borealis expert within the AVSO, and also our Landau lecturer at this year's AVSO annual meeting, he says that theorists predict that T Core Bor might produce observable neutrinos with current instrumentation, and so he's curious how SNEWS might handle it. And then he asks. And can you work with the neutrino experiments to use our knowledge in advance of time so that we can, uh, in time and direction, so as to push the neutrino detection threshold substantially lower? So since we know exactly where it is and that it might erupt, is there a way to, change the way the processing is done so that you can be more sensitive to that particular area of the sky?
Yeah. So I'll take the latter one first. So we will all get the neutrino burst from the core collapse at about the same time. So the neutrino detectors themselves won't have advanced warning. If it's lucky enough to be a few hundred parsecs away, and we're seeing pre-supernova neutrinos from it, then yeah, we. But of course that's not once or twice per century. That's much less. But if it did happen, we would have an idea of which star might be going boom. It probably wouldn't help us with our signal to background with supernova neutrinos very much, but it would be really cool. For T Core Bor, there are two things that make it very different than the core collapse supernova that we're looking at. One is the brightness, the luminosity is just way less. And so there are just simply many fewer neutrinos being spat out. And the other thing, which actually is probably harder, is that it's not very energetic neutrinos that are produced because they're really hot, cooling this baby neutron star. They are neutrinos popping out of the nuclear reactions from that shell burning that's causing the nova to burst. So it's more similar to solar neutrinos or neutrinos we see from reactors here on Earth. And there are an order of magnitude or more less in energy than these supernova neutrinos. And most of the experiments we have that are sensitive to supernova core collapse neutrinos just simply don't have a low enough threshold. You have to try pretty hard, and so experiments are able to see reactor neutrinos, for example, and by being very, very careful with background contamination and being deep underground. The subset of experiments which have that low of energy threshold is much smaller, and they themselves also tend to be less smaller. So again, taking the penalty on being able to see the fewer neutrinos. So I think most people would be really surprised if we see any neutrinos associated with a classical nova outburst. It's not going to stop us from looking, of course, because you never know if we're wrong. But I think the expectations are we won't see much, if anything, and if we do, it will only be in a few experiments.
Yeah, maybe a quick follow-up question to that is, aside from the sun, can you see any other stars in detectors, neutrino detectors?
No, we thought I ran the numbers once for Sirius, right? It's big and it's bright and it's kind of nearby and it's going to be hotter and yeah, no. One over R squared is a really harsh mistress. So
Yeah.
between one AU and even a few light years, suddenly you're toast for those kind of regular fusion neutrinos. Other things out there in the universe that we've seen in neutrinos, 1987A, we've seen the sun, and Ice Cube at the South Pole has seen a few neutrinos from blazars produced by the jets being accelerated by supermassive black holes that we happen to be staring right down the pipe of. And they are looking, of course, for more such things. And those neutrinos are very, very, very energetic, millions of times more energetic than the ones we're talking about here.
Yeah. Oh, cool. That's neat that we can see, it's mostly just high energy events aside from the sun that we can see is basically what you're saying there. Okay. Back over to Bert. So Derek here is curious if the SNEWS targets are actually listed in the AAVSO target tool, and if you should be going to that spreadsheet or going to the target tool to get information on what to observe.
So they are listed in both places. What the spreadsheet tells you is if someone has said that they're going to observe that star, or if someone has claimed a star, so to speak. It does not tell you if someone is actually observing that star or not. So that is one place where the target tool can be useful, is if you want to know like when the last time an observation took place on a star, you could go there and it would tell you. And they are visible. I believe there's a George can correct me on this if I am wrong. I think he is here. I believe there is a box in the target tool, or a box that you can click that will let you know what the SNEWS targets are specifically. If not, it's definitely listed in the notes field, and you can just type in SNEWS in the notes and it will pull up all stars that have that criteria listed.
Okay, terrific. Question back for Alec. Jeffrey Kassoff had asked a follow-up question to his previous one. He said, if only 1/6 of galactic supernova will be visible, then does it mean that the frequency of seeing one in the future is 1 of 6 to 2/6 per century?
Yeah, and I think that that 1/6 is easily visible. Like might be a naked eye object for humans, but you all watch things that are not naked eye objects all the time. So in terms of being able to see something with telescopes, if you know where to look, I think the answer is probably get a lot of them. Something right on the other side of Sag it's probably never going to see. Yeah, so and this matches, in fact, if you think about it, it's been 600 years since Kepler. And so those fractions you mentioned are kind of right on line with what expectations on average for what we might see. Yeah, with eyeballs, because it's only been in the past few decades that we've been able to see better, right? So
yeah. Brian Skiff asked a question which I think could be answered by either one of you, and he asks, given that we're suggesting people go and observe stars with kind of a 3-day cadence, what can observers really do that's not being done by some automated sky surveys like Assassin or similar surveys?
Well, the first thing to note is that Assassin saturates at about 10th magnitude. Maybe you can get down to 9, but it's a little bit untrustworthy if you go that bright. And for the main campaign, we specifically chose targets that are brighter than that on purpose, so that they would not be so that there wouldn't be significant overlap with things like Assassin. And I think Assassin is one of the brighter surveys too. I think most of the other ones are significantly fainter. The other thing with Assassin is that they only observe in the Sloan G band, which is sometimes good and sometimes not, depending on the sort of stars that you were looking at. So they used to be V specific, and now they're Sloan G specific. And depending on the target, that was either a plus or a minus. In a lot of the cases for the targets that I look at, the data got significantly worse in those cases. But that really just depends on what you really care about being sensitive to.
Okay.
And
so
you could also think we could also sort of double down on the cool ones, right? You're definitely these 200 that we're watching right now. You'll be able to see if they go off, right?
Yeah. Yeah, so it sounds like the objects that have already been selected for SNEWS are tailored to amateurs in such a way that they're producing complementary data to what sky surveys are producing, or it's already in the sweet spot, and so really they're amateur astronomers. This is really your time to shine, because these are the objects that sky surveys can't catch. Okay. Then Enrique here asks a question that's kind of a follow-up to what you mentioned in your talk, Bert, about AAVSO-net. What do people have to do in order to observe these stars using AAVSO-net if they're a member?
Yeah, so the easiest thing to do is on the spreadsheet, there's a place where you can put your name to request a star. And that's pretty much all you have to do to start off with. George is monitoring the list. And so he will take that name and he will move it over. If someone is already saying that they want data for this star, if they're not taking the data and doing something with it, George will, you can put your name there. And if someone drops off or someone's not processing the data, your name can get moved over. You'll get told about that. And then the data will be sent directly to your VFOT account. So you can get it all right there and do the processing all right there. And so it just sort of streamlines the process. And we did that for a couple of reasons. But one of the main ones was that we had multiple people putting in proposals for SNEWS stars, which was great. But a lot of them put in for the exact same stars. And so rather than sort of having all of the data go to specific objects, we thought it was better to sort of just decide we were going to observe all of the objects and then split the data up accordingly.
Okay, and a quick follow-up question still on the AAVSO-net topic. Are there any plans to coordinate SNEWS alerts or events to trigger AAVSO-net to follow up automatically?
Oof, I honestly cannot answer that question because I don't really have any control over that. Directly hooking in alerts into the AAVSO-net pipeline is not impossible, but it would require a lot of effort and a lot of time. And I don't know that anyone is really going to spend that effort and time to do. But if anyone is, it would be George. George Silvis does have the ability to do that. I don't know if he's going to take the time to do that because it's a significant effort to put something like that up. The telescopes are semi-autonomous now in that you get a schedule and it's sort of the scheduler will run and the telescopes are semi-remote in that instance. But the difference between that and getting an alert, judging the quality of that alert, and then pushing the telescopes out to there is a whole other level of effort.
Yeah, I did have a conversation with Bob Denny from DC3 Dreams. So if for those of you that are watching at home, AAVSO-net's telescopes use ACP as a scheduler, and so we have a human-managed queue-based system to start off with to decide like where to divide things and which telescope should get what work. But then ACP under the hood does actually support that alert-based systems through I think it's through virtual observatory events. So that might be something that we could consider integrating so that the telescopes, all go and focus on a single object if there is actually interruption. Okay,
Yeah,
so
and elaborate a little bit.
Yeah.
We have the capability of putting out VO events,
Mhm.
and of course, most of what we would do early would have error boxes that would make that useless. But we hope to be able to provide that as things zone in. And Danny Milicevic at Purdue in his refit system, which is a transient chasing, let's parcel out observing things to coordinate with each other based on your capabilities and things like that is working with SNEWS as well. And so we thought about how to do this, and we have some ideas, although it's not nailed down yet. And those will be exercised in these fire drill things that were mentioned earlier.
Okay. Yeah. Have you talked at all about the Sky Survey community and they have like a broker-based model for distributing, they're anticipating something like most Sky Surveys I've seen them quoting like we're going to be generating 100,000 alerts per night, right? And things like this Wiki Transit facility already have like a broker model in place. Do you have something similar like that for SNEWS?
Refit is trying to do that. It's not at that scale that
Okay.
the Rubin people, for example, are thinking about, but it's the same basic idea, yes.
Yeah, and speaking of Rubin, we got a good question here from Edward. He says, are the 192 targets too bright for the Vera Rubin Observatory to capture? And how many are within the sky area that Rubin will cover?
The short answer to the first question is yes. Ruben will be, I don't know what the saturation limit is, but definitely these stars are much higher than that. As to the actual coverage of Ruben, I don't know that I know the answer to that question. It is all sky, isn't it?
No, it's in the southern hemisphere, so
Oh, southern
it'll have
hemisphere.
a northern horizon limit at some place. Yeah.
Okay, I was unsure of that. I thought that they might have two telescopes. I couldn't remember. Um, yeah, so I couldn't tell you the total number that would be there. I honestly just don't know.
Yeah, I think the odds are with a lot of these larger, like professional observatories, right, that have, 2+ meter glass. It's going to be very difficult for them to be able to observe most of these objects. Yeah, that's a great chart to pull apart, Alex. So I'll pitch it over to you.
Yeah, so of course everything is in the galactic plane more or less, and so you get whatever you can get in the galactic plane, and southern hemisphere gets Sagittarius, so it probably does a little better than northern hemisphere.
Yeah, and do you maybe just talking about the distribution of supernova within the galaxy itself, right? There's more stars towards the center of the galaxy. So would you anticipate, more supernova in that region, or would they appear in the outer spiral arms? Where would you expect to see them distributed?
In the spiral arms, because it's pop two stars that uh, that are going to make the burnout die young big stars that go supernova, and things in globular clusters or in the bulge are pop one stars that have been there forever and aren't making new ones. So the spiral arms are the big areas.
Okay, yeah. So there's not really a huge advantage to the people that are in the southern hemisphere being able to see the galactic center then.
Yeah, but there are a lot of spiral arms that direction too. Just for
Yeah,
channel.
that's true.
So somewhere we have a plot of distance versus potential progenitors, and it's kind of fun. You can see the bumps of the spiral arms in that plot.
Oh, cool. So Patrick Kavanaugh here was asking whether or not data from tests or things that are pulled up through MAST might be useful in following up on supernova, or if it's just generally useful or too outdated.
Any data that we have from before the eruption is good, right? Like the more data that we have, the further back that we go, the better. The one caveat with something like TESS is that TESS is going to have very large pixels. So there could be some crowding confusion. If it's a smaller star that erupts, but it's near a larger star, it's going to be a lot tougher to disentangle what signal came from what object. So there is a little bit of that. But the sort of it doesn't really get outdated in this sense, right? Because any data that we have beforehand is good. It's just a question of like, when do we really start noticing these things? Like, is it 100 years before? Is it a day before? We don't have the data to realistically know. There are models, but again, all of those models are based on theories that are great in practice, but we don't have any real hard data to say for sure that this is definitely what's going to happen.
Mhm.
So
So maybe just asking, Thierry Midvein was asking kind of a very similar question here. He was just curious if the broader SNEWS collaboration intends on using any of the data that's been acquired by Gaia, for example, and folding that into their analysis.
Yeah. So
I
the
think Alec already mentioned that, right? About talking about, I'm assuming that you're getting the distance data from Gaia.
Well, there's distance, there's photometry, there's some spectroscopy there as well.
Yeah, and interestingly, I found out when asking a colleague who does this sort of stuff, how come we don't know how far away Betelgeuse is to like 30%? And the answer was, is it's way too bright for Gaia. But yeah, so a lot of these the surveys that give us these progenitors that let us say we saw about so many neutrinos, so 1/r² means r is about that far away, would be using exactly that data for the progenitor things. And after this thing goes off, everybody and their dog is going to be digging out every survey ever and trying to find all the data on it, which is exactly why your program is going to be so useful to everybody after the event.
Yeah, I was really quite surprised to learn that both, Gaia, I think it saturates at about 6 magnitudes, so it can't really give a very accurate distance to anything that's brighter than 6. Its predecessor, the Hipparcos satellite, I think it's saturated around 5 as well. So, the bright stars, their position is not known really well. And then even onto that, the baseline that Gaia has is about it's 1 AU, right? Because it orbits along with the Earth around it. And so any stars that have radii that are approaching like 50% of an AU, if there's any kind of like, photocenter or not photocenter, but if there's any kind of like spots on their surface or large convective cells, it yanks the photocenter around and then Gaia can't localize it. And so its error bars are going to be, about the same size as what the physical star is. So you get to anything that's about an AU, or like 50% of an AU or something, and the uncertainties on those stars go way up. And unfortunately, all of these red giants and these supergiants, like they're all in that category because they're several hundred solar radii, and so the uncertainties on their distances tend to be relatively high compared to main sequence stars.
Oh, I hadn't thought about that. So that's definitely true. And to follow up something you mentioned before, uh, there are theories and there are models of what goes on in really late stage red supergiants or very small stars, and they are all over the map. These things are super complicated, and the models are all over the map because the stars are, and the ones Bert showed today, they're doing things that we have no idea what they're doing. Okay, so exactly what we expect these things to be doing before they go boom is really the Wild West.
Yeah, we had a webinar several weeks ago with Dr. Arts, and I asked her a question about how astroseismic theory has been applied to, the things way off of the main sequence. And I don't recall her exact phrase, so you should probably go back and like look at our previous YouTube videos about that. But it was basically along the lines of our astroseismic theory doesn't really work up in those regions because we don't understand the physics of how the stellar atmospheres are coupling with the wind that's moving away from them. And so the data that you're collecting, even if the stars don't erupt, right? The data that you're collecting now could actually be very useful to the astroseismic community once they figure out the appropriate theories in that area. So I think the SNEWS campaign has a lot of applications for the photometry, just outside of the actual eruptions occurring. Okay, so let's go ahead and go back. I think there were a couple more questions about spectroscopy that were here in the queue. Wayne Green here is asking if low resolution devices like the ALPI or the SA100, SA200 would produce very useful data for looking at these supernova progenitors.
So the sort of thing that you'll get from the low resolution stuff here is you'll get broad indications of the star and some of like the really large lines or heavy emission lines or things if they exist or absorption lines. That's of actually pretty useful for the supernova itself, because you'll get sort of broad information about what's happening across the spectrum. I don't know how useful it is in general for before the supernova. Um, it doesn't hurt. It's kind of like having multicolored photometry in a sense. So you do get some information, but just a random, for instance, if you're just taking like one random spectra of a star, it'll probably be of limited use. If you were taking them a lot and you could show like changes in the continuum over time, that could be more worthwhile.
Okay. So then maybe asking a higher resolution question. So is there an optimal wavelength, maybe around H alpha, that people with high resolution spectroscopes should be looking at with the supernova candidates?
Oh boy, is that a question I don't have a good answer to. This is a little bit outside of my sort of expertise. I don't actually even know what is like really good to look at for supergiant or for these sorts of stars in general. Do you have any more knowledge on this front than I do, Alec?
No, M class spectra are a mess, right? And you might can you even see H alpha on those because there's all those really broad
They're so
molecular weights
red,
in the way.
yeah.
Uh, So yeah, I don't have a good idea either. And in all fairness, in graduate school, I did not take the stellar atmospheres elective because it was hard. So I'm the wrong guy to ask on this.
Uh, I would say like the person who'd probably be able to answer this question the best is Lauren, because she is both loves spectroscopy and read supergiants. So I will ask her after this if she has any good recommendations. And we will sort of, let people know. But honestly, I don't really know for sure. And even if it is a good thing to look at in general, I don't think we'll know from the supernova perspective of like what lines will really be the most impactful. Perhaps looking at like spectra from supernova 1987A, I'm assuming some exist, would sort of give us an idea of like maybe what lines might be important to focus on. But that's about all I can say right now.
And that one actually is a problem too, because it was had experienced a lot of mass loss and was back down to a blue supergiant at that point. So you were looking at all that interesting atmosphere had been blown away, and so the one we have a really good look at is a really weird one, unfortunately.
Yeah, I think I think we probably have lots of really good examples of spectra of a supernova after they've erupted, and so there should be lots of good examples of all sorts of emission lines and they'll be really broad, because there's a lot of material that's flying away at a whole bunch of different velocities. But before the eruption, that's a little bit harder question that I don't even have a really good answer to. So I would say um, maybe maybe good literature search might be appropriate, and maybe somebody could post something in the forums if they have time to go take a look at those things. So back to Alec here, I'll ask another question for you. So an anonymous individual here says, what is the rate of neutrino emissions from neutron stars after the supernova event in relation to the initial core collapse?
After a few minutes, a few hundred seconds, the neutrinos fall below what we could observe on Earth and probably just tank to nothing fairly soon thereafter. So even a really young pulsar like the crab isn't spitting out neutrinos right now from cooling. It's got jets, and so it might be doing some accelerator things in those nice jets you see in the high resolution pictures of it, but nothing that we can see here on Earth, unfortunately.
Okay. Another follow-up question for you. So in the case of supernova, the supernova in 1604, well, actually, sorry, I'll just read the question here directly from Diego rather than trying to interpret it. He says, after the last visible supernova in 1604 in our galaxy, are there any indirect signs that there's been any other supernova that have occurred? For example, like nebulae or bubbles or something like that.
Yeah, and just to be pessimistic, both Tycho and Kepler's supernova, I think, were type 1A and wouldn't make neutrinos. Anyway, they weren't core collapse or white dwarfs. And so this estimate of 1 or 2 per century is core collapse ones. The total is about twice that, but it would include white dwarfs going boom, which produce far fewer neutrinos. I think Cas A, if I'm not mistaken, that one is a supernova remnant that has a neutron star and is only a few hundred years old. Correct, Bert? I'm not a Cas A expert. And there was 1 or 2 others whose name is escaping me now, that when I asked this question of supernova remnant friends, they said, oh yeah, there's this one and there's that one. And I don't remember the names right now. I'm sorry, because that's the fun part, because you go and take a picture.
Oh, that's fine.
Yeah, I don't really know either, to be honest. Supernova are not really my level of expertise. After they explode, I'm interested.
Yeah, HB mentioned in the chat here that Cassiopeia A is about 350 years old based upon kinematics and light echoes. So that gives a little bit of an answer there.
And if I recall, no one is clear at all how come no one noticed and wrote it down on Earth, because they should have been able to see it.
Yeah. I am aware of a couple of large-scale H-alpha imaging surveys that are recently being released. So there's the MDW survey that was discussed at two of our AAVSO annual meetings ago, and they have really lovely pictures showing like bubbles in space. And I don't know if anybody's gone in and tried to mine those to correlate them with any kind of particular event yet, but they were coming up with 10 to 20 undiscovered voids, if you will, per month when they were first doing some kind of releases. So there should be some really interesting data that could be mined for that sort of thing. Question from our own George Silvas here. He says, is there a phone app that will notify people of events for SNEWS?
There is one right now, and it's only available on Apple because the developer, that's what he develops. Yeah, so if you look in the Apple Store, you'll find a SNEWS app. It's the same basic app as the gravitational wave alert app that the author said, oh great, it's easy to add another data channel to that, so I'll make a new app for SNEWS. And if you get that once a week, you will get our test, does everything, do the pipes still work notice. And in fact, HP has sent pictures of that showing up on his alarm clock, so it works. And once we start getting these other alerts from the new code in there as well, then we'll think carefully about how to use that for fire drills, for example, in a way which won't freak people out. That requires some thought.
Yeah, terrific. And then our last question is from Edward Lyons, and he's asking, why is Myra not on the list of SNEWS candidate stars?
That is actually relatively simple, because Myra is a red giant and not a supergiant. And while the difference might seem relatively banal, the actual difference is one of mass. So Myra will never go supernova because it's not massive enough to do so. It'll probably end as a white dwarf. Well, it will end as a white dwarf at some point. So that's kind of the difference. It just doesn't have enough mass to go boom.
Oh, terrific. That's an easy answer. So, well, we reached the end of our Q&A time. So let me go ahead and get the outro slides up here. First off, I'd just like to say on behalf of the AVSO, thank you for both Alec and Bert for coming and presenting at our webinar today. It's really interesting to see what's happening with this news campaign, and it's great to see that one of our flagship projects is being featured so prominently. So thank you both for showing up.
I wanted to thank
then, of
you
course,
all too, not just Brian, but all you AAVSO people who are out there taking observations. This is fantastic. It's so much fun to work with you.
Yeah, I've always enjoyed working with AVSO members, right? It's really cool to see people that are that excited to go out and in some cases freeze every single night while collecting data. I know it's a hard thing, but it's very worthwhile. And then of course I'd also like to thank all of our participants here in the audience. So as Alec just mentioned, right, it's you guys that make this stuff possible. And I think it's, when the next supernova actually occurs within our own galaxy, it's going to be amateur astronomers that are making some of the coolest observations and providing the most useful data to the professional astronomical community. So, please keep doing the good stuff that you're doing. I'd also like to thank our sponsor. As I mentioned during the beginning of the program, Boise Astro has sponsored the AVSO's webinar series for the entire year, and we're incredibly grateful for their generosity. And so if you don't know anything about them, the Boise Research Initiative and Education Foundation provides online astronomy, education, observing resources, and research experiences to students, teams, and schools to learn how to perform observations, conduct research, and publish their results in scientific journals, just like the Journal of the AAVSO. So please check out their website to learn a little bit more about their work. And then before we leave for today, I'd just like to remind everybody that the AVSO's next annual meeting will be held at the U.S. Space and Rocket Center down in Huntsville, Alabama. I mentioned the cool Saturn V thing, and I will say that every single time I have been in Huntsville, I have always gone down to the Space and Rocket Center because there's always something really new and interesting to go and see that. And I used to be in Huntsville basically, once every couple of months. The place never gets old. It's very, very interesting. So if you're interested in attending the AVSO's annual meeting, please check it out at avso.org/113. And then finally, just one final thank you to everybody who's been participating. Truly appreciate the time that you put in for collecting observations, and for Alec and Bert, thank you one more time for coordinating this campaign for the AVSO and also involving our participants. I'm sure that everybody is incredibly grateful. So with that, I'd say thanks for everybody, and we'll see you later.